Consider the following polynomial functions. What general observations can we make about both of these polynomial functions? We then want to go ahead and sketch a graph of each function separately. So looking at these two given polynomial functions, we notice that they're both quartic. In other words, they have degree 4. So your note is saying, so our general observations so both of these polynomial functions are degree 4. So we can say our degree n equals 4. So these are quartic functions, or quartic polynomials. Now we can make the following two conclusions about the graphs just based off of this degree. We can note that the graph of both of these polynomial functions will have at most 4 real zeros, which we know is equivalent to saying that the graph has at most 4 x-intercepts. Now keep in mind, this is not the exact number of real zeros. This is the maximum possible number of zeros that both of these graphs can have. So there could also be 3 x-intercepts, or 2 x-intercepts, or 1 x-intercepts. We won't know till we sketch each graph. And the second general observation that we can make is that the graph of both of these polynomial functions will have at most 4 minus 1, or 3, turning points. So this is not the exact number of turning points necessarily. This is just the maximum number of turning points. Now, in addition to these two observations, what else can we observe by looking at both of these polynomial? We see that, hey, they have the same leading term. So we can conclude the following about the leading terms of both polynomials. So we denote our leading term as a sub n times x to the n. So for both of these polynomial functions, the leading term is -1 times x to the 4th. And let's give ourselves a little bit more room. So we can see here that our leading coefficient is -1, which is less than 0. And we can also see that our degree, again, n is 4, which is even. So we can say that, therefore, by the leading term test, and I'll abbreviate LTT for leading term test, we can conclude that both ends of the graph, so both ends of each graph, point down. So in other words, the left-hand side of the graph points down, the right-hand side of the graph points down, but we don't know what goes on in between yet. So these are the two general conclusions that we can make for both of these polynomial functions. But now we need to go ahead and consider each function separately to help determine what exactly each graph will look like. So here we are considering the first polynomial function, f of x is equal to minus x to the 4th minus 5x squared. Now we already know from the leading term test that both ends of the graph are pointing downward. Now in order to sketch this full graph, we need to now go ahead and consider finding the zeros and then the multiplicity of each of the factors. So first things first, we need to find the zeros, or find the x-intercepts. So, in order to do this, we are going to set the function f of x equal to 0 and solve for x. So here we go. We have minus x to the 4th minus 5x squared is equal to 0. And we want a factor. So we can see that our greatest common factor here is minus x squared. So I factor minus x squared to the front, and that's multiplied by x squared plus 5 is equal to 0. Now, to even simplify this a little bit further, that negative 1 in the front, we can think of this as minus 1 times x squared. So we can go ahead now and divide both sides of this equation by negative 1, just to get rid of that negative. And we are left now with x squared multiplied by x squared plus 5 is equal to 0. So now by the zero factor property, we can go ahead and consider each of these factors separately. So our first factor is x squared is equal to 0, and our second factor is x squared plus 5 is equal to 0. Now, before we start solving, I want you to note in this first case that x squared is the same thing as saying x times x. So the factor we're working with here is x. Now, to solve for x, we want to go ahead and take the square root of both sides of this equation, which leave us with x is equal to 0. So there's our first real 0. And we could also, of course, write this in the ordered pair form, 0, 0. So now moving on to case 2, we have x squared plus 5. So, in order to start solving here, we will subtract 5 from both sides of the equation. So 5 minus 5 cancels itself out to 0. And we're left now with x squared is equal to negative 5. And so very similarly to case 1, if we try to take the square root of both sides, notice what happens. We're going to end up with x is equal to plus or minus the square root of negative 5, which we know we could separate to plus or minus the square root of negative 1 times the square root of 5, which produces imaginary solutions. Like the square root of negative 1 is the imaginary number I. So these are not real zeros. So that means they're not producing any x-intercepts. So we can disregard that factor. So the only factor that we are considering here is x. So let's think about its multiplicity. So we can conclude here that the factor x appears how many times? Well, as we stated above, we can see that this factor appears 2 times. So it appears twice, which means that it has a multiplicity, and I'll abbreviate for multiplicity, of 2, which is even. And so therefore, we know that the graph is therefore tangent to the x-axis at the 0. So it is tangent to the x-axis at x equals 0. So using this multiplicity and our 0, we're ready to go ahead now and sketch the graph. And so we'll give ourselves plenty of room. And so here we go. We are going to sketch the graph of this beautiful polynomial function. So we have the y-axis, and we also have the x-axis. So the first thing we want to reference is the leading term test. So from our leading term test, we know that both ends of the graph are pointing down. So I'll do my left-hand arrow pointing down and my right-hand arrow pointing down. Now we don't know what's going on in between yet until we start sketching the x-intercepts and we consider the multiplicity. So sketching our x-intercept, we know we have the x-intercept here at x is equal to 0. And we'll write that in its ordered pair form, 0, 0. Now, keep in mind from our multiplicity that we know that the factor x appears twice. So we have a multiplicity of 2, or an even multiplicity, which means that the graph is tangent to the x-axis at this point. So I'm going to put a little t here to help remind myself the graph is tangent there. Now, with just this information, we have enough to sketch a relatively accurate graph. But of course, if you want, you could plot a couple of extra points on either side of the zeros if you'd like. But again, this is all that we need to get a good idea of what the graph will look like. So to do that, remember that we always start reading our graph from the left-hand side. So this is where I'm going to start. So the graph is going to move up to that 0. Now, once we hit that 0, we want to consider the multiplicity. So since we know the graph is tangent to the x-axis at that point, that means that the graph must turn back around, moving to the other endpoint. And there you have it. Here is a beautiful graph of our quartic function, f of x is equal to minus x to the 4th minus 5x squared. Now, let's think back to the beginning for a moment. We know that this polynomial is a quartic function. So it could have at most 4 real zeros, and it could have at most 3 turning points. But looking at our graph here, we can see that there is 1 real zero and 1 turning point. They're the same point. We can see that this 0 is the turning point. That's where the graph or the function changes direction. And in this case, it's from increasing to decreasing. So this is an important example in demonstrating to us that while those 2 initial observations help to guide us, we can't make any final conclusions until we actually start sketching the graph. So now that we have the graph of our first polynomial function, let's go ahead and consider the graph of the second polynomial function. So here we go. We want to sketch a graph of the polynomial function f of x is equal to minus x to the 4th plus 5x squared. Now, we already know from our leading term test that both ends of the graph are pointing down. But what's going on in between? I don't know. Let's find out. So in order to do that, the first thing we want to do is find the x-intercepts, or those real zeros. So again, to find the x-intercepts, we are going to set f of x equal to 0 and solve for x. So here we go. We have minus x to the 4th plus 5x squared is equal to 0. And we want to factor. So looking at this, we have a greatest common factor of minus x squared. So we have minus x squared now multiplied by x squared minus 5 is equal to 0. And just like with the first example, I'm going to think about this negative 1. And to simplify this, I'm going to go ahead now and divide both sides of this equation by negative 1. So negative 1 divided by negative 1 goes to 1. And we are now left with x squared multiplied by x squared minus 5 is equal to 0. So this is almost identical to the last example we looked at, with the exception of this binomial. This is now x squared minus 5, which is a difference of squares. So we're going to need to manipulate this in order to apply the difference of squares formula. So we can rewrite this as x squared multiplied by x squared minus the square root of 5 squared is equal to 0. So now we can rewrite this as the difference of squares. This will be x squared multiplied by x minus the square root of 5 multiplied by x plus the square root of 5 is equal to 0. And the reason we're writing it out like this is so that we can really appreciate the factors and thus their multiplicity. So, applying that 0 factor property, we have 3 cases here. We have x squared is equal to 0, we have x minus the square root of 5 is equal to 0. And then we have x plus the square root of 5 is equal to 0. So in case 1, we have x squared equals 0. And if we take the square root of both sides, we are left with x is equal to 0. So that's our first x-intercept. In case 2, we can now add the square root of 5 to both sides of the equation. So these square roots of 5 cancel each other out, leaving us with x is equal to positive square root of 5, which is our second x-intercept. And in case 3, we can now subtract the square root of 5 from both sides of the equation. So the square roots of 5 cancel each other out, leaving us with our third x-intercept. X is equal to minus the square root of 5. So these are our 3 x-intercepts, and we can write them in their ordered pair form. So we have an x-intercept at 0, 0. We have an x-intercept at positive square root of 5, 0. And we have an x-intercept at minus the square root of 5, 0. So now that we have these 3 real zeros, we want to consider the multiplicity of each factor associated with them. So this is why it's so important to consider that fully factored version of the polynomial. So we have 3 factors to consider here. The first factor is x. And so looking back at this fully factored version, well, it looks like we have x squared. Keep in mind that that's just x times x. So this factor x appears twice, or 2 times, meaning it has a multiplicity of 2, which is even. So therefore, we know that the graph is tangent to the x-axis at x equals 0. So the next factor we need to consider is x minus the square root of 5. So looking back up at this fully factored version, we can see the factor x minus the square root of 5 is appearing 1 time. So this factor appears once, meaning it has a multiplicity of 1, which is odd. And so therefore, we can conclude that the graph crosses the x-axis at the associated 0. So the graph crosses the x-axis at x is equal to positive square root of 5. Now our third and final factor is x plus the square root of 5. So looking back up at the fully factored version again, we can see that we have the factor x plus the square root of 5 appearing 1 time. So we have the same conclusion that we had for above. So we can say that the factor x plus the square root of 5 appears once, meaning it has a multiplicity of 1, which is odd. And so therefore, the graph crosses the x-axis at this 0. So it crosses the x-axis at x is equal to minus the square root of 5. So we have everything that we need here. We have our 3 real zeros, as well as the behavior of the graph at these real zeros determined by the multiplicity. Which means we are officially ready to go ahead and sketch the graph. Woohoo! So here we go. And let's give ourselves plenty of room to sketch this graph. So we have the y-axis, and we also have the x-axis. Now, from the leading term test, we know that the graph, or both ends of the graph, are going to be pointing down. So here is our left-hand endpoint pointing down and the right-hand endpoint of the graph pointing down. So the next thing that we want to do is plot the zeros. So we know we have a 0, we'll say right about here, at minus the square root of 5, 0. And this has a odd multiplicity, so the graph is going to cross the x-axis there. We have a real 0 at the origin. And now this 0 has an even multiplicity, so the graph will be tangent to the x-axis there. And last but not least, we have a real 0 at positive square root of 5, 0. And this factor has, again, an odd multiplicity, meaning the graph is going to cross the x-axis there. So, we are ready now with just this information to sketch a really accurate graph. So as always, we keep in mind that we read a graph from left to the right. So we're starting with the left-hand side of this graph. And from this point, we want to move until we hit that first 0. And the graph is crossing right through the x-axis there. Now this graph is going to have to turn around somewhere so that I can hit the next 0, which has an even multiplicity. So this means that the graph is tangent, so it bounces back up. And again, it has to turn around somewhere around here so that it can hit the next 0. And because that 0 has an odd multiplicity, the graph crosses right through the x-axis there. And there we have it. This is this graph for the polynomial function f of x is equal to minus x to the fourth plus 5x squared. So notice the difference with this graph from the previous graph. This new graph has 3 zeros. 1, 2, 3. This graph also has 3 turning points. We have a turning point right here. This is where the graph or the function is changing from increasing to decreasing. We have our second turning point here at the origin, where the function changes from decreasing to increasing. And we have our third and final turning point right here. And this is where the function changes from increasing to decreasing. So the moral of this example is that while we can use the degree of our polynomial function to determine the maximum number of zeros and the maximum number of turning points, the only way to really simplify this process and to determine exactly what's going on is to sketch the graph. So we can make those general observations at the beginning, but we're always going to want to take it an extra step further and find the exact zeros for your polynomial function, and then use the zeros and their corresponding factors to determine the multiplicity and thus the graph's behavior at each 0.